So the first thing, we'll get the homework. All right? I know you're already giving it to Rob in Johnson City. I sent the other back to you, right? Yeah. So, a couple things here to start with is the capstone. We're down to the last problem. We're going to work on it tonight. Right, this is due on Friday the 4th at 11 a.m. Right, you're going to upload the Word document, upload to D2L, Dropbox. I think it's titled Capstone Project also, right? So then that'll take care of that. And then this is due at 11 and 11:30. You'll see some solutions show up. You want to go look at those solutions before you take the final. Right? Not that you're concentrating on that. It's just, there's some questions on your final. There always is on the final that come off of your capstone using that data and everything. Okay? And then the other thing I have is our final is Thursday the 10th. That's next Thursday, and we're from 6 to 8. That's at night. Okay? Now, here's the deal. All right? If you're in section 521, which is you folks there in Sam Wilson, you are going to go to Gilbreth, .306, and Rob will be there with you. I have a reason for us moving around. If you're here with me in Kingsport at 531, you're going upstairs to room 336. So we're all moving all over the place. And if you're in section 990 and you told me you were going to Johnson City, because I'm going to assume that you're going to do the same thing for the final that you did for test 2. If you told me you're going to Johnson City, you're going to Gilbreth 106. If you told me Kingsport, you're going to room 336. And if you're using a proctor, I'll be mailing it out probably next Tuesday evening, the 8th, right, to your proctors. Okay? Now, you need to bring an ID and a calculator. I will provide you with the formulas and tables. You folks that are using a proctor, you need to take an ID, a calculator, and your formulas and tables. They'll know you're coming with that. Okay? Now, the reason for all this movement is we want information about the final. We want information from, like what grade you make, what problems you miss. And the easiest way for us to do this is to have you put your answers in D2L after you've taken the test. You're still going to have the test in hand. You're still going to have an answer sheet. You're still going to write your letters on there just like before. Except when you're done, there's a computer going to be sitting in front of you. And you're going to put your answers in D2L for us. And then the nice thing is, when you submit your answers, you're going to get an immediate grade. You're going to know exactly at that moment what you made on the final. That's kind of nice. Okay? So what I wanted to show you is what you're going to do is in D2L, right? So I'm in our little site here, the 521 one. You're going to go to Evaluation, Assessments. All right? So the little forms for the different tests, there's more than one test in the room. There's actually 4. Okay? It's under Assessments. And what you're going to see here is there'll be a maybe. No. Thank you. Assessments. you'll see there's 4 forms. There's a Form A, there's a Form B, there's a Form C, there's a Form D. On the top of the front of your test, you're going to have a form, right? It's going to be Form A, Form B, Form C, Form D. And so when you go into D2L under evaluation assessments, you'll pick the form, right? Whether you're Form A, Form B, Form C, Form D. If you pick the wrong form, yeah, it should be all screwed up, okay? What I'm going to show you is, look, there's nothing here. I'm going to show you the preview of this. This is going to require a password. The person that's in the room with you will have the password, right? So you'll put the password in, okay? Tonight, of all nights. Unbelievable. You'll put the password in, and then it'll open up. So, look, I'm going to bypass all that, and I'm going to start the quiz to show you what the little form looks like. Look, there's no answers there. The only thing there is your answer for number 1 is A, B, C, D, or E. Your answer and you'll click the right one, okay? And then, you can save each question as you go, or you can just, at the bottom, you're going to submit, right? There's 43 questions on your final. We count it like it's out of 40. So there's 3 bonus questions there. Tonight. Mind your tongue, son. It says it recommends to save at every point. Look, there's not going to be a rush here at the end. You're doing all this when it's all over with. You've already got all your answers. You're just logging in here. You're picking your form. You're going to put your answers in, and it'll immediately grade it, and then we can get the information, the data we want from the test. All right? Please? Pretty please. That's the story. That's the reason we're moving all over the place. Not because you need Minitab or anything crazy like that. It's where you're going to put your answers in for us. All right? We'll check back on this in a second. Now, I'm going to remind you this again on Thursday at the beginning of class where everybody's going. I'll put it up in D2L, like on the first page there. It shows up in your in the class site there so that everybody knows where they're going. All right? This works fine. It's just like any other test. You still got an answer sheet and everything, so no problem. So the thing looks like this when you go in, right? You get the password. Your answer to question 1 is you pick A, B, C, D. You can save at each point. So there's no answers there. You're just putting the letter in, right? Whatever you chose on your little answer sheet. And then at the bottom, notice there's 43 questions. At the bottom, you just go to submit the quiz. Tell it, yeah, I want to submit the quiz. It'll grade it. It'll give you the grade. I'll see everything. Everything's good. Okay? That's what we're going to do with the final. Now, what we have left to do here is I'm in Chapter 20, and this was Inference in Practice or something like that, right? It's the inference about a population mean. So here's what we're going to do. The last thing I wrote up for you last Tuesday was we're looking at this, and the catch is in this chapter is we don't know sigma. This is what separates this from the 2 previous chapters to this. All right? Is we no longer are going to be given the standard deviation of the population. We don't know sigma. All right? So, the thing is, we estimate sigma with, now that little s there, that's the sample standard deviation. That's what we're looking at. We have a sample. We can calculate the standard deviation from it. That's the little s from back in Chapter 2. You know, where we use Minitab to calculate the standard deviation for us? That's what that is. In other words, what I'm telling you is, this is your parameter. I'm not doing this to freak you out here. And this is your statistic. Remember, nobody said that the parameter had to be a population mean or a population proportion. Hell, it's a population standard deviation. Right? So we will calculate the appropriate statistic from your sample. Well, it'll be the sample standard deviation S. You know, just like you want to use X bar to estimate mu, we'll use S to estimate sigma. Now, if we do that little move, then what we do is we estimate sigma over the square root of n. Remember, that shows up all over the place. When you're looking at the sampling distribution of x bar, that's its standard deviation. We estimate that standard deviation with okay, throw an s in there. S over the square root of n. S over the square root of n is called the standard error of x bar. Now, you saw me do that in chapter 22, right, about proportions. We estimated that standard deviation with the standard error. We're doing it again. Now, this little story here is on page 456. This idea of this standard error, this idea of estimating sigma with s. Sigma over the square root of n by s over the square root of n. Now, here's the thing. That doesn't seem like a big move here. And what I mean is, instead of it being a sigma, now it's an s. Okay, I changed the frickin' letter. I went from something I didn't know to something I can calculate from my sample, right? Okay? So, doing that, we're going to have to talk about something called t distributions. The reason I put an S there is there's not one, there's many. There's a whole bunch of these t distributions. Now, I'm going to do it to you like this. When we know sigma, right? When it was given to us in the problem, we use a z-score. Right? That's the one we use. That's what we were using before, right? It has the standard normal distribution. What I'm talking about is it's normal with a mean of 0 and a standard deviation of 1. That's the one you've been using since we first saw the sampling distribution of x bar. We used it when we talked about confidence intervals, test of significance for mu where sigma was given. There's only one standard normal. It's the table A that's in the back of your book. Okay? When we use the standard error, s over the square root of n, to estimate that standard deviation, we no longer get a z-score. We get a t-score. And its t is equal to x bar minus your mean. So when the sigma becomes an S, when you have to estimate the population standard deviation, you no longer get a z-score. You no longer get the standard normal distribution where the z-scores live. Now you get a t-score, and it lives under some t distribution is where it lives. Okay? Now, the next sentence I'm going to write, I haven't said this to you all semester. This does not have a normal distribution. That's a first. All right? This t-score here, this idea of estimating, with S using estimating sigma, you don't get a normal distribution. Okay? It has a t distribution. Now, there's nothing special here. All this stuff I'm telling you is on page 457 in a box here. It says, draw an SRS of size n from a large population that has the normal distribution with mean mu and standard deviation sigma. The one sample t statistic. You know how you had a one sample z statistic, your z-score? Now you have a one sample t statistic. That's exactly what I have there. T is equal to x bar minus mu over divided by s over the square root of n. Has the t distribution with n minus 1 degrees of freedom. Now, remember, in Chapter 2, S comes with degrees of freedom. DF is what I called it. And I told you in Chapter 2 that every time you calculate a standard deviation from a set of data, right, from a set of observations, or in this case from a sample, it always comes attached with this degrees of freedom to it. And it's always one less than the number of observations. It's always one less than your sample size, right? So it's always equal to n minus 1, where n is your, in this case, your sample size. Then what the little box is trying to tell you is when you pick out the right t distribution, you pick out the t distribution with n minus 1 degrees of freedom. There is a different t distribution for every sample size. And the way you pick out the one you're going to work with is based off of the degrees of freedom. And it's always one less than your sample size there, right? In other words, there is a t distribution for each sample size. If you're looking at a sample of size 50, then we know the degrees of freedom is 49. You'll be looking at the t distribution with 49 degrees of freedom. Okay? Now, the notation is like this. I don't know if you'll ever see the notation outside of this book, but we always use the t distribution. I always just put n minus 1 here, where n is your sample size. So if you had a sample of size 50 and you want to know what t distribution you work with, it's t distribution with 49. It's t with 49 in the parentheses. If you have the degrees of freedom, you know the sample size. It's one more. If you've got the sample size, you know the degrees of freedom. It's one less. Okay? So there's one for every sample size. Now, other than that, okay, when we estimated, when you estimated sigma with s, sigma over the square root of n by s over the square root of n, that standard error, you no longer get a z-score, you get a t-score. You no longer get the standard normal distribution, you get a t distribution, and the one you're working with is t with the particular degrees of freedom that's one less than the sample size that you are looking at. All right? Now, here's the thing. I'm on the bottom of page 457, and I want to look at figure 20.1 there. There are three density curves. There is the standard normal one, which is the solid one. That's the z-scores. That's where we are used to seeing. There's the one with the big dashes. That's the t distribution with 2 degrees of freedom, which means you had a sample of size 3. The one with the little dots, that is the t distribution with 9 degrees of freedom, which means you had a sample size of size 10. Right? When I look here at all three of these at one time, they look the same, right? One of them is the standard normal. That's the solid. The other one is the t distribution with 9 degrees of freedom. That's the little dashes. The other one is the t distribution with 2 degrees of freedom. I know n is equal to 10 here, and n is equal to 3 there. Okay? They all look the same. They are centered at 0. In other words, the mean of each one of those three density curves there is 0. They're all single peaked. They got a single hump in them. And they're all symmetric. So on the face of it, you can't distinguish between the standard normal and a t distribution with 2 degrees of freedom, 9 degrees of freedom, 27 degrees of freedom. They all look the same. They're all centered at the same spot. They're all single peaked. They're all symmetric. They're all bell-shaped. 2. What is different between the 3? Well, you notice the standard normal is up here. The one with 9 degrees of freedom is a little lower, and the one with 2 degrees of freedom is a little lower. Now, they're density curves. They all have area 1 under them. Okay? The spread of a t-distribution is greater we're estimating the standard deviation. The spread is greater greater than this one, the standard normal distribution. The way I like to think about it is a t-distribution has more area in their tails out here, right? So the standard normal sitting here, the t-distribution is not as tall, but the area still has to be 1 under. There's more area in the tails of a t-distribution, okay? And that's because you are estimating sigma with S. The other thing to notice here is as the degrees of freedom increases, that means as your sample size increases, the t-distribution gets closer to the standard normal distribution. Why is that? Well, we have a little thing called the law of large numbers that says, as your sample size increases, x bar gets closer and closer to mu. What the law of large numbers really says is as the sample size increases, your statistic gets closer and closer to the parameter you're trying to estimate. So as the sample size increases, as the degrees of freedom increases, S becomes a better and better, closer and closer to sigma. So you're getting better and better measurement of the spread there. So the t-distributions will get closer to the standard normal. Now look, I'm going to go back over these one more time. Number 1, they all look the same. That's what I'm telling you, and they're all centered at the same spot. They're all centered at 0. They all look the same. Number 2 and number 3 go hand in hand here to me. In number 2, what I'm telling you is the t-distributions do not satisfy the 68, 95, 99.7 rule like a normal distribution does. They are not normal. They look normal. They don't have 68% of the area, 1 on either side, 95, 2 on either side, 99.7. There's more area in their tails. They're flatter and more area in their tails. Why? Because you're estimating the standard deviation, and the standard deviation is what controls this. And then number 3 is as you start taking larger and larger samples, the t-distribution looks more and more like the standard normal. In other words, it starts doing this. It starts getting taller, and it gets less and less area in the tails. Okay? That's what number 3 is. Now look, other than that's what's going on in this chapter is we didn't know sigma, so we estimated it. Now we don't get a standard normal distribution, you get a t-distribution. We're not doing anything by hand, so you just have to know where things are coming from. The interpretations I'm getting ready to throw on you for the confidence intervals and the test of significance are exactly the same. The software is going to calculate the confidence interval for you. The software is going to calculate the p-value for you. You got to know you're looking at t-scores and a t-test statistic. The interpretation is the same of both of them, right? Whether I knew sigma or not. Okay? Now, here's what I'm thinking. I just told you the 2 things we're going to do here, right? And so I'm on page 459. And it won't be long here before you see me work out a problem using the software and interpret it for you. On page 459, there's the one sample t confidence interval for mu. Now, it's a t because we don't know sigma. Before it was a one sample Z confidence interval. Okay? And it looks like this. There's your estimate, plus or minus. Normally that's a Z star, right? That's a critical value based off the standard normal, and then S over the square root of N. That's the formula. You're not going to use it, right? We're going to get the software to do it for us, but that's what it looks like. Okay? Notice that's an estimate plus or minus a margin of error again. X bar is still your estimate. The margin of error is T star times sigma over the square root of N. Okay? Look, 1 second here. If you want to think about what that T-score is measuring, remember a Z-score measures what? It measures how many standard deviations away from the mean a particular observation is, right? You know, you're 2.2 away. That means you were 2.2 standard deviations to the right of the mean. The T-score is not telling you how many standard deviations, it's telling you how many standard errors away you are. So if you see a T-score of 2.7, that means the observation, right? Your X bar was 2.7 standard errors greater than the mean, because you're measuring in terms of standard errors with the T-score. That's the deal. Okay? That's my formula. Before we do a problem. Okay? I want to go to the next thing. I want to go to page 461. And I have a one sample T test for a population mean. Not a Z test. There's not a Z score involved. That's not your test statistic here. Your test statistic is going to be a T score. Now, the reason I wrote the page number down, I'm on page 461. There's a box there. This is the third time this dude picked this box up and reprinted it. Now, he might have changed little letters in it and stuff, but he reprinted it. It says, draw an SRS of size n from a large population with an unknown mean mu. To test the hypothesis that the null is that mu is equal to some value, that's the same as before, right? That's the same when we were talking about the mean before. Compute the one sample T statistic, right? So this is your one sample T statistic. This is your test statistic. It is a Z-score. Okay? It's calculated as X bar minus mu sub naught. Now the reason I'm using that mu sub naught is because the null is mu is equal to that mu sub 0. Remember, we assume the null is true to get the test started. And then you divide by that standard error. That's the new part, that it's a T-score now. Do you see the three pictures there, the three different alternatives, greater than, less than, or not equal to? You still find the p-value the exact same way. You still interpret the p-value the exact same way. Okay? Now, what I wanted to look at is, I want to look at this problem here, 20.2. I'm going to back up another page. So, in 20.2, they've got, it says, let's look again at this, the study of tipping in the restaurant we met in example 16.3. We follow the four-step process, that's fine. Does the expectation of good weather lead to more generous behavior? Psychologists study the size of a tip in a restaurant when a message indicating the next day's weather would be good as written on the bill. Remember, we talked about that somewhere. Okay? Here are the tips for 20 patrons. You've got a sample size of 20 here. Okay? It says, this is one of 3 sets of measurements made, the others being tips when received the bill, the not good, nothing on the bill. We want to estimate the mean tip for comparison with tips under the other conditions. Plan. We will estimate the mean percentage tip mu for all patrons of this restaurant that received the message on their bill indicating the weather will be good. I want a confidence interval. I want 95%. Now, you know, normally as I was doing the confidence interval, I'd be telling you to write the Z star down. No, we're not writing anything down. I know what confidence interval I want here. It says we must first check the conditions for inference. Can we consider this a simple random sample? Remember, that was the one where we always start. It says, as in chapter 16, we'll regard these as an SRS. That's a good thing. Okay? Now, here's the deal. Nobody's going to tell you the population distribution is normal at this point. The only thing you got to work off of is the data. And so you can make The data, you're going to make one of two things. You're going to make a stem plot or you're going to make a histogram. And then based off of what you see in that, if you don't see any bad outliers or bad skewness, you're going to say, yes, we can assume that normality condition. Because that's all you got to work on. Okay? It says, the stem plot in figure 20.2 does not suggest any strong departures from normality. There's a possible outliers. Things look roughly symmetric, right? We feel pretty good about using it. That's all you have is the data. So you look at the data by making a histogram or a stem plot. You're looking for something that looks single peaked, roughly symmetric, and you don't want any crazy outliers in your data set, right? I'm telling you, there's one to worry about here at 27. Okay? The other things look okay to me. And then it says, okay, we can proceed to calculate the data. Here's what I'm going to do. I got Minitab up for us, maybe. Okay? I'm going to come over here, and I'm going to find us this file that goes with this. This is chapter 20, correct? And the file is the tips. Yep. All I'm doing is I'm a lazy man's way, and I'm putting the data there, right? There's those 20 different percentage of tips that's in the book there, right? Okay? Now, what do I want? I want a confidence interval. I'm going to go to stat, basic statistic. You've already seen me use that one sample Z, the fourth one down. This is a one sample T. All right? I'm going to go to one sample T. Now, I got some choices. Do I have the summarized data? In other words, do you have the sample size, X bar, and S? No. I got the raw data, right? One or more samples in each column. That's what I have there. I want to go to I want to put my variable in here. My variable is the percents, right? I'm going to go to options. Now, I can put any confidence level in there you want. The problem asks for 95%. Yes? The one thing you want to make sure of when you're asked to calculate a confidence interval, and the reason I'm being so slow here, you still got learning curve things to do, right? And there's still stuff out of these chapters. Now, you can use Minitab to calculate confidence intervals and do the test, because we're not doing it by hand. Okay? You always got to make sure when you're doing a confidence interval that the alternative is a two-sided. It's always set as two-sided when you go in there, but if for some reason you did a test, make sure it's always set at two-sided or you won't get a confidence interval. Okay? So if I click two-sided, I click OK, I click OK, it comes back and tells me your sample size is 20. The mean of those 20 percentages is 22.21. That's exactly what the book has. The standard deviation is 1.963, exactly what the book has. You see that standard error in of the mean? That's S over the square root of n. They took that standard deviation and divided by the square root of 20. They figured out what that standard error was for you. And then your confidence interval is 21.292 to 23.128, which is exactly what they have here, 21.29 to 23.13 rounded off. The software gave you the confidence interval. We are 95% confident that the true mean tip percent when the bill says good weather the next day is between 21.29 and 23.13. The interpretation is exactly the same. It's can you read the printout? Where did it come from? There it is. Okay? It's exactly the same. Now, not every problem do you have the raw data. Right? There's problems in your homework, and I'm sure there's problems with the learning curve. You don't have the raw data. If we go back here to stat, basic statistic, one sample T. Instead of telling it I got the sample in each column, let's say I want to know I have the summarized data. They want to know what's your sample size. My sample size here was 20. The mean here was 22.21. The standard deviation is 1.963. Now look, the reason I'm doing this is I'm showing you either way. If you've got the summarized data, in other words, you don't have the raw data, you've got the sample size, the sample mean, and the sample standard deviation, you can do it that way. I'm going to go to options here, make sure I'm 95, not equal to two-sided alternative. I click OK. You won't notice any difference. Hell, it's the same, right? It can go either way. If you've got the summarized data, you can do this. If you've got the raw data, you can do this. Okay? Now, what about a test of significance here? Well, I'm going to do the one that's in the book again, 20.31. Excuse me, 20.3. And it says this. It says, to investigate water quality on August 8, 2010, the Columbus Dispatch took water samples at 20 Ohio State Park swimming areas. Oh, that explains it. Those samples were taken to laboratories and tested for fecal coliform, which are E. coli bacteria found in human and animal feces. An unsafe level of fecal coliform means there's a higher chance that disease-causing bacteria are present and more risk that a swimmer will become ill. Ohio considers it's unsafe if a 100 milliliter sample, about 3.3 ounces of water, contains more than 400 coliform bacteria. Okay. Plan. Experts caution the tests are a snapshot of the quality of the water at the time they were taken. Fecal coliform levels can change as weather and other conditions change. So we asked the question in terms of the mean focal coliform level, mu, for these swimming areas. The null is the level is not unsafe, and the alternative is the level is unsafe. In other words, the null is mu is equal to 400, and the alternative is mu is greater than 400. Safe, not safe. And the question wants to know is, based off of your sample, do you have evidence that the waters are not safe on average there? Okay? It says these swimming areas have been deemed safe in the past, and the reason the data was collected was determined to continue to be true. All right. So there's 20 pieces of data here, right? I can see it right there in the solve part. N is equal to 20. Okay? It says, are these data good evidence that on average the fecal coliform levels in these swimming areas were unsafe? That mu was greater than 400 there. Yes? So we're going to check the conditions. Simple random sample. They're going to give me a yes on that. That, yeah, we'll assume this is a random sample. The next question is, I write it as normality. Remember, it's got to be roughly symmetric. No big outliers. So you're looking at figure 20.3. What do you think? I don't see any outliers this time. What's that histogram look like to you? A little bit skewed to the right, maybe? Yeah? A little skewed to the right here, yes? It says, here's the way this guy gets around this. First, check the conditions for inference. We're willing to regard these particular 20 samples as an SRS from a large population of all possible samples. Figure 20.3 is a histogram of the data. We can't accurately judge normality from just 20 observations. There's no outliers, but the distribution of fecal coliform tends to be somewhat skewed. Yeah, it seems to be somewhat skewed to the right. What does that mean about my test of significance? Right? Based off of that 20, things aren't as good as I'd like to see them be. Are we going to continue? Yes, we are. Okay? Now, I'm going to come over here, because I'm not going to do this by hand, to get my T-score, my test statistic. Open. What's this one? This one is water quality. Look, in this table here, that's just the 20 that's right there. Okay? I'm going to go to Stat, Basic Statistics, one sample, T. Now, I know this time I have the samples in a column. It is your fecal coliform. Okay? Now we want to do a test of significance. So it says perform hypothesis test. Any window you're looking at where you're doing Minitab to do a test, where it says the hypothesized mean, that's the null hypothesis. And in this case it is 400. How do I know that? I wrote the hypotheses down for you before, right? And then we're going to go to options. This time, I don't care about the confidence level. You're doing the test, right? You have to pick the appropriate alternative. And the alternative is, what was it? It was greater than 400, correct? I want that one. I want greater than. Okay? I click OK. It comes back and tells me the sample size is 20, the mean's 1231, the standard deviation is 1038, the standard error, the mean's 232. Your T-score here is 3.58. So here's what I'm interested in. My T here is 3.58. My P is approximately, or is actually equal to 0.1. Now let me ask you that. Is that a large t-score or is that a small t-score? T-scores operate just like z-scores. Would a 3.85 z-score be large? Yeah, this is a large t-score. Is that a small or a large p-value? Look, you know how I always number things? There's your number 1. There's your number 2. There's your number 3. Your number 4 is, what are we going to conclude here? Well, you're going to what? Let me ask you this. Do you want to reject H naught or do you not want to reject H naught? You got a small p-value. When you get a small p-value, what do you want to do? I want to reject H naught. That's my typical kind of statement here. Are the data statistically significant at the 5% level? Yes. Are the data statistically significant at the 1% level? Yeah, because your p-value, hell, it's 0.001. Obviously, 0.001 is less than 0.01, 0.05, or any other significance level you'd want to do. What does it mean in this case here to reject H naught? What do we have strong evidence of? Let me ask you this. Do you want to be drinking the water? Maybe I should put it to you in something you want to think about. Do I want to drink this freaking water from these 20 places? And I'm thinking, I don't think so, right? So we have strong evidence. That the water, I was getting ready to say something bad. That the water tastes like crap. That the water is unsafe. Now look, this could have been a problem in a previous chapter. If somebody had told me what sigma was, we could have done this before. See, here's my point. Whether you know sigma or not has nothing to do with stating the hypotheses, right? That mu was 400, that was safe. Mu was greater than 400 is not safe. That's got nothing to do with whether you know sigma or not, whether you estimated it, or whether you have a t distribution or any of that. Except here, when I'm checking the conditions, you don't have sigma. So you know it's got to be a t, right? This has to be a t test. So we have to get the software to spit out the t to us. Rob, you still there?
Yes, sir.
That's cool. All right. So you have to have the software to spit the t out to you. It'll spit the p-value out to you. Did I interpret this like any other p-value that was small? Yeah, I want to get rid of the null hypothesis. We got strong evidence in favor of the alternative. We got strong evidence that this water is unsafe. It's the same. Okay? Now, one more thing here. All right? Right here. If I go back here to this basic statistics, one sample t, could I have done this with the summarized data? If they'd have gave me the summarized data, yeah, you can do it either way. If you have the raw data, you can do it. If you've got the summarized data, the sample size, the x bar, and the s, you can do the problem by choosing summarized data and putting in what n is and so on and so forth. Okay? Now, before I do the problem on the project, there's two other little things here. And I'm on page 467. Yeah, and I'm going to keep referring you to page numbers. There's matched pairs T procedures. Now, remember, matched pairs, that's a type of experimental design, right? Where you matched your subjects or you treated these subjects as a pair. There was only 2 treatments allowed, right? So if you want to talk about matched pairs T procedures, how do we deal with a matched pairs experiment where, okay, I've got to use T, okay? We're going to find the differences between the two treatments. Remember, matched pairs, there's only allowed to be two. And apply the one sample T procedures that I just showed you how to deal with. Right? So you're not working with the data, you're working with the differences between the two treatments, right? You're doing a subtraction here. Maybe it's a before minus an after, or it's this treatment minus this treatment. Okay? That's what you're going to do here. Now, I just get tired of always doing the problems. I'm going to do the one about the chimpanzees, 20.4. Okay? Look, I just need something so I can show you the software here. Right? That's what we're using. It says, humans often collaborate to solve problems. Will chimpanzees recruit another chimp when solving a problem requires collaboration? Researchers presented chimp subjects with food outside their cage that they could bring within reach by pulling two ropes, one attached to each end of the food tray. If a chimp pulled only one rope, the rope came loose and the food was lost. Another chimp was available as a partner, but only if the subject unlocked a door joining two cages. Chimpanzees learn these things quickly. Okay. The same 8 chimpanzee subjects faced this problem in two versions. The two ropes were close enough that one chimp could pull both, no collaboration needed, or the two ropes were too far apart for one chimp to pull both, collaboration needed. Table 20.1, page 468, shows how often in 24 trials for each version, each subject opened the door to recruit another chimp as a partner. Is there evidence that these chimpanzees recruit partners more often when a problem requires it? In other words, are they smart enough to know they need to collaborate? Right? That's what we're asking. Is there evidence? So you got a table here. You've got, what is this? 1, 2, 3, 4, 5, 6, 7, 8. You got a sample of 8 different chimpanzees. And they did this multiple times, right? You notice the first one, collaboration needed. Yes, 16 times. No, 0 times they asked for help, right? They recruited a partner. Now, here's what we want to do. I want to set up a test, and I'm going to do it like this. The differences that I'm looking at is I'm going to take collaboration, minus not. That's what they did, right? They took 16 minus 0, look at 16, 16 minus 1 is 15. That's the differences, okay? So I'm going to do that. And then if I want to know if they are smart enough to know that they require, remember, when I'm stating the hypotheses about a mean, they look like that, okay? Now, the question says, is there evidence that chimpanzees recruit partners more often when a problem requires collaboration? That mu would be greater than 0, right? That they would recruit a chimpanzee more often when it required that. That means this is equal to 0. Now, all I've got is the raw data there. Okay? I'm not going to find, they've got the differences for me. I'm not going to do this by hand. What I'm going to do is I'm going to come over here. I'm going to find this problem, hopefully. Okay? See what the data looks like. The chimps. Now, something I want you to notice here in this table. They didn't do the subtraction for me. I got each one of them, right? The ones that said collaboration was needed, yes, no, right? On that. So I don't have the differences. So when I go to stat here, basic statistics, you'll notice there's a 1 sample Z, 1 sample T, 2 sample T, there's paired. When you don't have the differences, you got to do the paired part here. Okay? So I got to do the paired. It says each sample is in a column or summarized data. No, I don't have the differences. I have each sample is in a column. Sample 1 is the collaboration. Sample 2 is no collaboration. I'm going to go to options here. It wants to know confidence interval, Sure, we'll do 95%. At this point, you can put anything in there you want. Notice at the very top it says the difference is the mean of sample 1 minus sample 2. So whatever you put in is sample 1 minus sample 2. It's collaboration minus not here. Okay? I want to do the hypothesized mean is 0. How do I know that? Mu is equal to 0. I want, for my alternative, I want greater than, right? Remember? Mu was greater than. They asked for help. I'm going to click OK. I'm going to click OK. Now, it gives me all kinds of information here. It gives me the mean of the collaboration, 19.63. The mean of no collaboration, 7.25. The standard deviations, the standard errors. It gives me the differences. It does everything for me. Then it says, forget that 95% lower bound. It says a t-test of mean difference. Because that's what you're looking at here. You're trying to estimate the mean difference. Okay? Is equal to 0 versus greater than 0. Your t-value is minus 7.37. Your t is minus 7.37. Your p-value is, I can't write 0. I got to write, I know it can't be exactly 0. Oh, I just went back here and looked to see what it told me, right? My t-score was minus 7.37. That's my test statistic. My p-value here is virtually 0. There's your 1. There's your 2. There's your 3. 4. What do you want to do? Is that a small p-value? It don't get no smaller than that. You want to reject H naught. What do we got strong evidence of here? We got very strong evidence this time. Very strong evidence that a chimp will collaborate when needed. Right, because that's what the questions asked me here. Is there evidence that chimpanzees recruit partners more often when a problem requires collaboration? Very strong evidence that a chimp will collaborate when needed. That's it. Okay? Now, one other thing here. Okay? Same thing here. I could, look, here's the deal. Some of the problems, they just give you the differences. And they give you the mean of the differences and the standard deviation of the differences. Then you do the one sample t. Right? So you put the differences there. Okay? If not, we can do the paired. If you've got the summarized data, notice how the summarized data comes to you. This is all about the differences, right? Sample size, the mean, standard deviation. You can do it whether you have the raw data or whether you have the summarized data. Okay? Now, here's what I want to do. I want to come to here. This is the one problem we haven't done. It says to earn a bachelor's degree, you need to accumulate 120 credit hours, approximately 40 courses. In order to graduate in 4 years, students should take 15 credit hours per semester. Do ETSU students take an average of 15 credit hours per semester? It says, created a suitable graph to display the distribution of hours reported by our sample of college students and inserted here. What's your graph here? What's your choices? This is a histogram, right? I want to make a histogram here. Okay? I want to come over here. I got this guy here. I'm going to make a histogram. I just want a simple one. What am I looking at? The hours that they take. There's your histogram. Copy, paste. Got to look at it. Hang on to that thought. Describe the distribution shown in your graph. You see any possible outliers? You see any skewed to the left, maybe? Yeah, right? This is a little skewed to the left, and we got some possible outliers here, yeah? That's the kind of thing I'm looking at. That's what you're looking for here. It says, perform a test of significance to see if ETSU college students have similar credit hours per semester to the average college student. If this claim is true, if they have the same as other college students, then the average hours reported by ETSU students should be 15. In other words, the null should be that mu is equal to 15 if they're the same as the average college student. For this test, the null hypothesis is that the average hours reported by ETSU students is what was reported for the average college students. That is, mu is equal to 15. Write the correct alternative hypothesis for the test. Now, did they tell us to pick a side? Did they say greater than? Did they say less than? Every problem we've seen always says greater than, less than, different. When they don't tell you what to do, when they don't tell you to pick a side, you always use the two-sided test. You would use not equal to here. If you see a problem in the homework, or you see a problem on the learning curve, or you see a problem on the final, and they don't pick a side, you always do the two-sided test because you're picking both sides then. We're not picking a side, so we're going to go two-sided. So you're going to put there mu is not equal to 15. It says use Minitab to perform the appropriate test, copy and paste. Okay, there was my graph. I'm going to go to stat, basic statistics. That's a one sample t problem. You know how I know that's a one sample t problem here? Does anybody see sigma given to you? Nope. Is it about a population mean? Yeah. Is sigma given to you? It's got to be a t. That's how you know. All right? So I want to go to stat, one sample t. This time I want to put in here hours. Notice I don't have the summarized data. I got the raw data. I got everything in one sample, right? What do I want here? I want, what's the value in the null? It is 15. We're going to go to options. What do I want here? What I want it different, yes? We want it different there. So I want the alternative to be different. I'm going to click OK. I'm going to click OK. Now, you got a sample size of 814. Your mean is 14.23. Your standard deviation is 2.65. The standard error is 0.0930. There's your confidence interval, 14.05 to 14.41. Your t-score here, your t-test statistic is a minus 8.24. That's freaking gigantic. That means that mean of 14.23 is 8.24 standard errors smaller than the mean. Is that a large or a small test statistic? That's gigantic test statistic. Your p-value here is virtually 0. So you're going to cut and paste that, all that right there. You're going to cut and paste it, right? Copy and paste. What is the name of your test statistic and what is its value? You're looking at a t, right? It's a t-score. It's a t-test statistic, and its value is minus 8.24. What is the p-value for your test? Well, shit, we just read it. Hell, it's going to be in D. It's 0. All right? It says, state your decision regarding the hypothesis being test. Do you want to reject H0 or do you not want to reject H0? We want to reject H0. You got a p-value of 0. You don't believe the null. Hell, you believe the alternative. We want to reject H0 based on our sample. It says, state your final conclusion, use complete sentences. Well, look, based on our sample, we wanted to reject the null hypothesis, right? We don't believe that mu is, I'm giving you more than one sentence. We don't believe that mu is equal to 15. We believe that mu is different than 15. Yes? Another thing you could say at this point is, we believe that ETSU students are not taking the number of credit hours as the average college student. We believe it is different from the average college student. We can't pick a side. We did a two-sided test. All you can tell me is we believe that ETSU students are taking a different number of credit hours than the average student. That's your statements to be made here. Okay? Now, is the p-value valid in this case? Do we trust it's what we're asking you? What assumptions are we making in order to carry out this test? What's the first assumption always? What's the first condition always? We're assuming that ETSU students represent a simple that our sample is representing a simple random sample of ETSU students. That's the first thing. We're making a gigantic assumption that our data came from some simple random sample. The sample size here is 814. Life is good. Now, before I finish this, I'm going to leave this right here. I'm going to come back here, and I'm going to take you to page 470. The book talks about robustness of T procedures. And what that means is when you start violating the conditions, like a simple random sample, you see skewness, you see outliers, how much do you trust your confidence interval, or how much do you trust the p-value? That question right there that I got. And so on the bottom of page 470, it says using T procedures. You got to know this box, folks. This tells us when we're allowed to do what we just did. It says, except in the case of small samples. A small sample is less than 40. All right? The condition that the data are in SRS in the population of interest is more important than the condition the population distribution is normal, roughly symmetric and no outliers. If you're less than 40, you got to pay attention. If you're bigger than 40, it's more important that you had a simple random sample. Now, we're going to break it up into three pieces. If your sample size is between 1 and 15, let's say 2 and 15, you can't get away with anything. If you see any skewness or any outliers, do not pass go. Can you use the T procedures? Yeah. Do we trust them? Not one little bit. Between 1 and 15, you can't get away with shit. Right? No outliers, no skewness. Between 15 and 40, that's the next step. I can get away with a little bit of skewness and a little bit of outlier. I can't get away with any strong outlier or any really bad skewness. So here's the deal. Between 2 and 15, you can't get away with anything. Do not pass go if you see any kind of skewness or outliers. Between 15 and 40, you can get away with a little bit of skewness and not a real bad outlier. Bigger than 40, it's more important that you had a simple random sample. Go at it. So back here, your sample size is 814. You think we cared that it was skewed a little bit to the left and there was possible outliers? The sample size is 814. That's bigger than 40. It's more important that you had a simple random sample here. So that was our biggest assumption we were making to make this p-value be valid, is that that our sample can be representative of ETSU students. It's going to be a simple random sample of ETSU students. The sample size is 814. Life is good. It's a little bit skewed to the left. I didn't give a shit. My sample size was 814. All right, there was possible outliers. My sample size was 814. It's bigger than 40. That's what that little box is telling you. Now, the reason I'm warning you about this, I've seen this happen on the final. We give you a problem here where it's a one sample T, right? You're trying to do a test of significance or something. And they give you the histogram. And the sample size is like 15. And you see some bad skewness, left or right. You see some bad outliers. Right? And then they go through and do the work for you. Oh, hey, you get a p-value of 0. What do you want to do? I want to reject H naught. No, you don't. Dude, you can't trust that p-value because your sample size was only 15 or whatever, and I got bad skewness. I got bad outliers here. You weren't allowed to use the T procedures. Right? So you've been warned. Now, does that take care of our project then? Okay. The next thing we need to do. Look, I know students don't like it when I pull out the software and all that, but look, there's no need for us to sit here and beat our brains out. I just want to make sure that you can read that. Can you read that? Like if that showed up on the test, can you read that? That ends 814. Hey, what's the degrees of freedom here? In other words, what T distribution is Minitab working with to find the area in the tail? It's working the T distribution with degrees of freedom 813. Right? It's always one less than your sample size. So that's what Minitab did. It drew out that nice T distribution. It found the area to the left, and it doubled it. Right? Because it's a two-sided test. You can always tell you're looking at a two-sided test because you see right where it says one sample T, hours, that's your variable. You see where it says test of mu equals 15, that's the null. Versus not equal to 15, that's the alternative. Yeah? It tells you. You read it, it's there. Even in those other ones I was showing you, it was there like that, okay? Now, the other thing we need to do here a little bit tonight is we're going to go to the next chapter. I'm going to be worse in the next chapter about using the software than I was in this one. You're not going to see me write any formulas down. You know, at least I wrote the T-score for you, and I wrote down the formula for the confidence interval. You won't even see me do that here, okay? Because at some point, you just got to say, okay, the interpretation is the same. What the hell are we trying to interpret? What's my test of significance look like? Okay? And so on and so forth. So, there's chapter 21. Look, if I thought we were missing something, you know I would tell you, right? Like if there was something I wasn't covering or I wasn't doing, you know, just because I went through that rather quickly. The reason I can go through that rather quickly is because we didn't calculate by hand. The interpretation is the same. I don't know how many times I've said that tonight, but it's the same. The p-value still means the same thing. The confidence interval is still the same thing. The only other warning about chapter 20 was when we were looking at matched pairs, we're looking at the differences. That's what we're working on, right? And you're always talking about the mean of the differences, right? I have a reason for telling you that, you know, you were trying to make a claim about the mean of the differences. You're trying to estimate the mean of the differences. The wording matters here. Because when I get to chapter 21, it says comparing two means. Uh-oh. Now there's two of everything. There's two populations. There's two population means. There's two population standard deviations. There's two samples. There's two sample sizes. There's two sample means. There's two sample standard deviations. There's two of everything now. There's not one population. Everything we've done up till now, there's been one population and one sample. I don't care if it was about a mean or about a proportion. There was one. Now there's two. And what we want to do is we want to compare the mean of this population with the mean of this population. All right? Now, when I think about two sample problems, the first thing we have to be able to do is identify a two sample problem to know that we are looking at two populations. Okay? So we've got two populations or two treatments, not matched pairs. And what we want to do is we want to compare these two. Right? We want to compare two populations or we want to compare two treatments. Okay? The catch is this. We have separate samples. We have two independent samples. In other words, no matching. The other thing is, there's two populations. You're going to take a sample from here, and independently you're going to take a sample from here. A separate sample from this population and one from this. The other thing is, can be different sizes. You can take 50 out of this one and 20 out of this one. They don't have to be 50 and 50. You can have a sample whatever size out of this population and a sample of whatever size out of this population. Okay? Now, if I take a look here at page 486, I want to look at the apply your knowledge problems. Okay? It says, which data design in each situation described in exercises 21.1 through 21.4 requires inference about a mean or means, about a mu or a mu1 and mu2. Identify each as involving a single variable, matched pairs, two independent samples. The procedures of Chapter 20 apply to designs 1 and 2. We're about to learn about the ones for design 3. So are we looking at a one sample problem, a matched pairs problem, or a two-sample problem where there's two populations. So if I look at 21.1, it says choose 10 agricultural plots of land located in different regions of the state. Plant half of each plot with one variety of sweet corn and the other half with a different variety. Compare the sugar contents of the varieties of corn. That's a two-sample problem, right? We got this sample, I got this sample. There's two. 21.2, exercise and memory. To examine the effects of physical exertion on the memory of a witnessed event, researchers randomly divide police officers into two groups. One group completed, 21.1 was matched pairs. I was thinking 21.2. That's matched pairs, right? You've got this part, you got half and half. You got this one half and half, right? So the plot, you got half and half. 21.1 was matched pairs. I apologize. The other one, we divided police officers into two groups. One group completed a high-intensity physical assault exercise, and the other did no exercise. Both groups were then placed in a live, occupationally relevant scenario. After the scenario, the mean scores on the exam, testing, and recall of what was witnessed during the scenario were compared. That's a two-sample problem. This group did the exercise, no exercise, and then we put them in there and we wanted to compare, right? That's a two-sample problem. There's two different populations, the one that exercised and the one that didn't. 21.3. To check the lifetime of a new battery in a soon-to-be-released smartphone, an engineer surfed the web over 4G continuously, beginning with a fully charged battery until the battery was drained. The engineer repeated this a total of 10 times. That's your sample size, 10. He compared the results with a lifetime of 20.8 for the current battery used in the company's smartphone. Is there two of anything here? Are we matching anything? That's a one-sample problem. That problem right there could have been in the previous chapter. You're comparing the mean lifetime of this battery with what the current battery does, 12.8. 21.4. Another engineer is checking the lifetime of a new battery with a prototype that she just developed. She wants to know how the lifetime of the new battery and her prototype compare. New battery prototype, right? It says she measures the lifetime of the new battery and her prototype for continuously surfing the web over 4G until the battery is drained. She repeats this a total of 10 times for each battery. You got a sample here, size 10. You got a sample of size here, size 10. You're going to take the average and you want to compare these two means, right? The old battery, the prototype battery. That's a two-sample problem where there were two different batteries involved here, okay? Now, here's what I want to do, all right? Comparing two population means. The starting point is this. Make a stem plot or a histogram for each sample. Just like in the previous chapter where you had a single sample, you were going to make a stem plot or a histogram and start looking for skewness and possible outliers. Now you've got two samples. You're going to make a stem plot or a histogram for each one of them. And what you want to do is you want to compare shapes, centers, spreads of both samples. So you're going to have a stem plot for each sample. You're going to want to compare them. You want to look at the shapes, the centers, the spread, any possible outliers going on. Now, I'm on page 487. It says condition for inference comparing two means. So my conditions here, well, if I got two samples, how many SRSs do you think I should have to have? I need two simple random samples from distinct populations. I need them to be independent. In other words, by knowing who is in one sample tells me nothing about who is in the other sample. I mean no matching allowed. The reason I keep referring back to no matching, because sometimes when you look at a problem that's matching, it looks like a two-sample problem. It's not. You need two separate samples, two SRSs from distinct populations. They need to be independent of each other. No matching allowed here. 2, both population distributions need to have similar shapes. That's a different story. No strong outliers. 3, means and standard deviations are unknown. The reason it's plural is there's two populations, there's two means, there's two standard deviations. Now, I'm going to do it like this. Just for the sake of things, I got population 1 and I've got population 2. This one has a mean, that one has a mean. They're subscripted by the population that they are dealing with. This one has a standard deviation, this one has a standard deviation. This one here we're going to choose a sample size, this one here we're going to choose a sample size. This one here we can calculate a sample mean, this one here we can calculate a sample mean. This one here we can calculate a sample standard deviation, this one here we can calculate a sample standard deviation. There is 2 of everything. There's 2 distinct populations, there's 2 samples, there's 2 means, 2 standard deviations, 2 sample means, 2 sample standard deviations. Okay? Now, if we want to work with these, now, you noticed before I had, when I was talking about matched pairs, it was the mean of the differences. Now it's the difference of the means. Where that word difference goes makes a difference, right? I'm not looking at the mean of the differences. Now I'm looking at the difference between the 2 means here, right? Population 1 and population 2. Okay? So, to do, look, you folks understand we're going to use that to estimate that. That's going to estimate that, right? This is going to estimate this. See, the mu's and the sigmas are parameters. The x bars and the s's, those are your statistics. So we always use our statistic to estimate our parameter. It just so happens there's 4 parameters and there's 4 statistics now. And it don't make a shit. There can be 22 parameters and 22 statistics. I don't care. As long as I got something to estimate my parameter, I'm good to go here. Okay? Now, to do inference, confidence interval, test of significance. To do inference about mu1 minus mu2, the difference of the means. Again, the language makes a difference. We start with, well, what the hell would you use to estimate that? The difference of the sample means. In other words, if I want to estimate the difference of the means, that's going to be my estimate, the difference of the sample means. Okay? Now, Debbie? 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 Ah. Okay. So, here's what we're thinking about. 2 sample T procedures. Up till now, it's always been a 1 sample Z or 1 sample T that we just talked about in the previous chapter. Okay? Now, I don't want to get too carried away here, but we're going to use the difference of the sample means to estimate the difference of the population means. We use exactly what we think we should use at this point. Okay? Now, obviously there's a standard error here. There's a standard deviation we wish we could use that we can't calculate. Okay? So, there's a standard error here, and it's the standard error of the difference of the means is this. Look, what you're doing there is, remember, it was usually sigma over the square root of n, right? When you have two populations and two means, you add those together, right? So that would be my little standard error over the square root of n. The standard error of the standard deviation of the sample mean, sample 1 divided by the square root of n. We squared them all there, and we added them together. That's like your standard error here. This has the same kind of standard error as the other problems did, right? The previous chapter. Now, with that, we get a two-sample t statistic. I got to write this down. T is equal to that divided by the standard error. So what this is doing is, this measures how far the difference of those sample means, how far x1 bar minus x2 bar is from 0 in standard errors. Now, we're going to pick up there on Thursday. I need to show you a little bit of problems here. We need to decide on degrees of freedom because you notice I'm using a t here. There's a t distribution again. What's the test look like? And then how do you interpret a confidence interval? All right? So get your homework back. Be careful going to the house. We'll see you on Thursday.